So pretty much, this part of the course, as briefly alluded to last time, is related to it's related to geotechnical design, not necessarily geology, like what's in your midterm. So geotechnical design involves a couple of things, but essentially it's making sure that as engineers, the ground in which we do our construction and build our projects is sufficient, right? So we're basically making sure it has enough strength and isn't going to settle enough such that our buildings are ruined, basically, right? So essentially, we're talking about earth structures. So this is kind of leaning towards my specialty, which is like structural engineering. So this is the interface between all like the geology stuff that you've been learning and like how it relates to a building, right? So a structure. Okay, thank you. Okay, so earth structures include, we're going to cover 3 types of earth structures in this course, right? We're going to talk about shallow foundations, deep foundations, and retaining walls, right? So shallow foundations will be covered in week 7 and week 8. So we're going to split it up into this week and next week. So in this week, we're going to be talking about bearing capacity, right? Which is basically how strong is the ground underneath this pad footing. And then week 8 is about settlement. So how much is the ground going to move underneath this foundation? Yeah, how much is it going to move, basically, right? And then in week 9, the lesson which I won't be here, they're going to talk about, whoever's the tutor is going to be talking about deep foundations. In other words, you basically have, how do I say this in broad terms? Okay, in week 9, they'll be talking about both the bearing capacity and the settlement. But the topic's actually quite easy, at least from how we learn it in this course. So it will be combined into one lesson. And then in week 10, we're going to be covering retaining walls, right? Which is also quite a loaded topic. And yeah, so really there's only 4, question?
Sorry, you said now you're not here.
Yes.
I'm just wondering, are you going to get married? Are you going for a wedding or something?
Thank you. No, I'm not getting married, but I have a mandatory like induction thing for my PhD.
I thought it's a wedding, so you have to invite us to your wedding.
I've never had that question before in my workshops, I can't lie. Okay, no, I'm not getting married. All right. So retaining walls, right? Yeah, we'll cover that in week 10, all right? I'll be here for that one. I won't be at a wedding. Okay, so let's talk about the focus for today's lesson, right? So we're going to talk about bearing capacity specifically. But before I can talk about bearing capacity, I need to tell you what is involved in shallow foundations, right, basically. Okay, so here's some examples of shallow foundations, or there's some examples of foundations in general, right? But a shallow foundation is basically something that is shallow, so it's not embedded very deeply into the ground. And they come in a few forms, and there's a couple of reasons as to why they occur, okay? So the idea for an individual column footing is if you imagine a building, right? And let's just say it's a very simple building, it's got 4 columns, right? Now, if the ground underneath it is generally pretty sufficient, right? You can get away with using pad footings, okay? I've been calling these pad footings. Sometimes they're called spread footings. I think the most common word in industry for it is pad footings. So you might choose to do that. So you kind of want to start with the most elegant, simple design, and then you only go to a more complicated design if you have to. Okay, so that's the most simple type of footing. Okay, so say instead of columns, right, you have walls, right, which need to be supported. So walls are basically 2D versions of columns, right? So they're taking all this load. And so the load is distributed along the line, right? So it makes sense that naturally you would want to put a strip footing, right? They call it a wall footing. I've only really heard it called a strip footing or a ground beam. Sometimes it's called a ground beam. But yeah, I think it's called a strip footing, right? So something that's rather long. So like basically, if we call this dimension B, the width, right? and this dimension is called L, right? So usually in like geotechnical design, we're gonna call the dimension which is longer L, right? So if we're looking top down, right, and we have a width and a length, the dimension that's longer is L, and the dimension that's shorter is B, which is width. Okay. So strip footings is basically where L is significantly larger than B, right? That's just general definition for it. Okay. You can also have these other ones where you combine footings. So say, for example, there's a really bad patch of soil underneath this building right here. Okay. You might want to, one way around it is you might want to combine these two footings together. Okay. So it spreads out the load. So that would be a combined footing. There's different types of combined footings. It's basically the same thing, but you might decide to turn it to a different shape, such as this one. If you combine enough footings, that's called a mat footing. And a pile foundation, which brings me to my next. Yeah, it's kind of interesting, right? So when we're talking about deep foundations, right? So why would you ever have a deep foundation? Okay, so if you've got a building, trying to think of how I'm going to draw this. Okay, so that's the building. We're looking at it side on. Okay. Say the ground underneath the first 6 meters is really bad. It's really poor. Okay. It's like a really weak fill. So even when you step on it, you can see it squash down. That's how bad it is. Okay. But then underneath there, you've got rock. Okay. So under 6 meters, you've got rock, which is a lot stronger than soil. Okay. So what you might choose to do, instead of relying on a pad footing, which is going to settle a lot and it's going to have very low bearing capacity because of that weak soil, you might decide you want piles underneath your building. Okay. So yeah, and we won't talk about piles because I won't be here for week 9, but I'm just going to leave it at that because there's quite a few things to talk about. I will upload a recording, so you can watch that if you want to know more about piles. But the idea of a pile is something that's sometimes called a pile cap. Okay, so if you've got a pile, so here's your pile. Let's say it's circular. Okay, at the top, sometimes you might see something called a pile cap, right? Which is, it looks somewhat similar to a pad footing, and it's just like a rectangular block that sits on top of the pile. So there's a couple of reasons why you might want to do that. The first one is eccentricity. So say for whatever reason you can't land a column directly onto your pile. You might want your column might have to sit here for whatever reason. Okay. Then you might want the pile cap on the top to transfer the load basically from the column into the pile. Okay, so that's one reason you might do it. Then another reason you might want a pile cap is if you have multiple piles and you want to combine their strength, right? So, and then say the force does land directly in the middle. You've basically engaged 4 piles through one really, really heavy column, if that makes sense. So there's many reasons why you might have a pile cap, but a pile cap is not the same thing as a pad footing because it's mostly to transfer loads from a column into the piles. But it effectively, rather than like relying on the bearing pressure here. Yeah, okay, I'm not going to talk too much more about that. Hopefully that kind of gives you a summary of why you might see pile caps. Yeah, just briefly, there's a few ways you can form piles. A pretty common way is you see like a drill that drills down a hole. So if you've done, say, like woodworking before, right? You can pre-drill a hole into your wood, and then you can drive like a screw into it, for example. That's basically what a pile is, at least a board pile. So the idea of a board pile is that drill bores a hole, and then you fill it with your reinforcement and concrete. So it's a board pile. Another way you can like create a pile is if it's precast, So the concrete's already been formed, and it can be rectangular or circular. You can bang it into the ground, like basically a hammer and a nail into wood. So that's called a driven pile, I believe. Yeah. Anyway, there's some differences, but you'll learn it in week 9, okay? Retaining walls is basically if you have two different elevations of soil and you want something that stops the soil from up here from collapsing, that's a retaining wall, okay? So these are the kind of earth structures that we're going to learn about, but I won't talk too much longer about this because we've got a lot to go through actually. Okay, but do you guys have any questions firstly? Because I want to give you the context, like this is why this is important, right? Okay, yeah, good. Okay, so pretty much when we're calculating the capacity of shallow foundations, I don't know why I decided to order my notes like this. Like I made these notes a long time ago, so it makes no sense, right? So there was these two researchers who were like pretty, give me one sec. I was asking AI about this because I was interested myself. Okay, so there were two researchers, right, back in the day who were like cornerstones of geotechnical research, right? One guy's called Terzaghi, 1943, he produced a paper, and then another guy's called Hansen, okay? And then 1970, he built upon this dude's formula, okay? So for bearing capacity, Terzaghi, he basically made like a model which represented how strong soil was, right? In the context of shallow foundations, right? And this was his formula, okay? So he made 3 different types of formulas for 3 scenarios, right? One where you have a continuous footing, which is a strip footing, right? So like that. That's continuous footing. One's a square footing, right? So your pad footing. And then one's a circular footing, something like that, right? And then he basically said there's 3 components to this, right? There's your cohesion component, which gives you bearing capacity. There's surcharge, and I'll explain these probably later. And there's a portion due to self-weight or unit weight, okay? So these 3 things basically contribute to how strong the ground is underneath your footing, okay? And that was in 1943, okay? So the reason we never see this anymore in modern day geotech design, so like I say rare, but like I made these notes way back then. Basically, we never see this like ever. So you won't expect to see this in your finals because this was superseded by another guy called Hansen, right? So Hansen built upon this formula and added additional variables to it, okay? So the idea about behind Hansen's formula, right? So Hansen made 2 formulas. One's for undrained saturated clay, okay? The other one's for the general equation, right? So it's probably better to talk about the general formula first. I don't know why I ordered my notes like this, right? But I'm going to talk about the general formula first because there's quite a few things that he packed into this formula, right? And it accounts for all kinds of different niche scenarios, right? So the first thing is he consolidated the idea of different types of footings into a shape factor, okay? So you don't need 3 different types of equations. You just have one modification factor that changes it. And it's called shape factor. It's called S, okay? The second thing is he introduced something called depth factor. Because in the Terzaghi equation, it doesn't account for, I'm trying to look for the right word. Give me one sec. Sorry. One sec. Foundation embedment, okay? So depth factor accounts for foundation embedment. So what does that mean? Basically, if this is a surface, right, and your foundation's up here, right, it's not embedded, right? There's no additional soil, how do I say this? no additional soil. But the soil, as you go deeper into the ground, is stronger, right? So if you go deeper with your foundation, you have more embedment, right? And so more soil around it is going to help confine it, basically, right? So that's the idea of depth factor, which was introduced, right? So that's D in all these. So you'll see these 3 times, right? So shape factor is seen 3 times, depth factor is seen 3 times, right? And then he also introduced 3 more niche things, I would say, right? So the other niche things are I, G, and B, okay? So what do these stand for? I is the inclination factor, G is the ground factor, and B is the base factor, okay? So essentially, these are all to do with different angles, right? So that's the thing that ties these 3 things together. So basically, there's a diagram for it. The I factor is to do with an inclined load. Okay, well, this is a bad example because it has all 3 on it at once, right? So just imagine you have a foundation like this, okay? And your column is raked. In other words, it comes in at an angle, like here, okay? So you basically have a force, right, from your column, and it can be broken into 2 components. That's a bad color to use. It can be broken into your vertical component and your horizontal component, right? So that's the idea of inclined factor, right? It accounts for inclined loads. Because normally columns want to deliver your load vertically, right? But basically, with the Hansen equation, it accounts for a partially horizontal component, right? Okay, another thing is the ground factor, which is to do with the slope of the ground on which the footing is built. In other words, this one, okay? Oh, no, sorry. Wait. This one. Okay, so basically, if you have a foundation like this, and the ground next to it has an excavation, that angle, we call it, I think it's psi, this one. That's related to your ground factor, right? So if you have an excavation, it takes away from a bit of the confinement next to the footing because the soil is on like a slope over there. Okay, and then another one is your base factor. So this is to do with the angle of your building, basically, right? So this slope, we'll call it eta, I think. This one. The weird looking N is eta. So that angle is like the angle in which your building is built, right? So that's the base factor. Okay, so yeah, there's 3 correction factors, and these are kind of niche things that you might see in various questions that they might test you on. But usually only one is included at a time because they take extra time to solve, if that makes sense. Okay, does anyone have any questions about how these factors work? Okay. So there's like a shitload of information basically that's presented in front of you, right? And upon your first time looking at it, you're like, do I really have to plug in an equation with 20 variables? But the truth is that most of these can be canceled out. And that's the point, right? So like all the questions that you're gonna see today, like 50 to 70% of these factors get cancelled out. So you just need to know what gets cancelled out. And that's the trick, right? So if you don't know what gets cancelled out, you run out of time in your finals, and then you can't solve the question in time. So yeah, you just have to have an understanding of what's actually going on. Okay, so I'll explain cohesion, surcharge, unit weight, and these factors soon, right? So these were part of the original equation from Terazaghi. But it's really just a matter of reading from a table, so it's actually easier to explain if I just show you in a question. I do want to talk about something called effective width though, okay? So one thing that's rather important to know is if you have a foundation, right, like this, and say your column load isn't exactly in the middle, right? So if that's the middle of your column, if that's the middle of your pad, and your load's applied here, okay? So we basically have something called eccentricity, right? So if this pad is 2 meters wide, right? basically we have an eccentricity here, let's say of 0.5, okay? We have to use this formula to find the effective width, right? We go B minus 2E, okay? So then we just plug in for E, for example, we might put in 0.5, and for B we put in 2, okay? So that gives us an effective width of 1 meter, right? Basically, if you have a concentrically loaded column, pad from a column, that utilizes the majority of the pad, right? But as soon as you have eccentricity, or the load is applied slightly offset from the middle, it's actually worse for your bearing capacity, okay? You generally want to avoid this unless you absolutely are forced to because of, say, architectural limitations or whatever, or you're at the boundary of your site and you need to have the column in a certain spot. Okay. Any questions about that? Yeah, the reason I am talking about effective width at the moment is because you'll see that pops up in the next thing I'm going to talk about, and that's the effect of groundwater. Okay, so groundwater basically is when you have a water table underneath your ground. Okay, so let's say that's your pad, and your water table can do something like this, let's say. Okay, so if it's at the surface, right, your entire pad is submerged, right? If it's way down here, right, I'm going to exaggerate it by quite a bit. If your water table's really, really far beneath your pad, we say that, like under drained analysis, the water table doesn't affect the pad's bearing capacity at all, okay? But if it's kind of near your, like the base of your footing, but like isn't completely submerging it, right? Then we have to basically say that it's partially submerged, okay? And there's an interpolation formula for it, okay? This is the, okay, so basically, okay, let me just show you what I've written before, okay? So under drain analysis, if your water table is above the footing base, so I've drawn it like this, but your footing base is here actually. So even if the water table is here, it's technically considered as submerging all your soil, okay? So in the case where your soil is submerged, you have to do an effective unit weight, which removes the portion of your water weight, okay? So subtract 9.8 kilonewtons per meter cubed, okay? And then, yeah, when the water table is way below, it doesn't affect gamma at all. You're just gonna use whatever you were given for gamma. But when water table is somewhere in between, you have to use this interpolation formula. And this interpolation formula uses these two things, okay? So I need to explain what, basically, the depth from the surface to the base of your footing, we call that uppercase D, right? So that's the depth of embedment, right? So from the surface of the soil to the base of your footing is uppercase D. Now from, in this particular formula, right, from the base of your footing to the top of the water table, right, that is lowercase d, okay? So that's how you have to interpret these formulas. Because basically that's lowercase d, and if that number is less than your effective width, then you have to apply this this formula basically. And we just talked about effective width, and it's to do with your column eccentricity, right? Okay, does that make sense? I've got one more thing to talk about, and I'll give you guys a quiz, all right? Oh, and whoever wins the quiz, the 3 people, gets a Coca-Cola. Okay. All right. Last thing I want to talk about is dry loose sand. So dry loose sand has a different failure mode to all the other types of soils that you'll see, okay? We basically, for most of these soils, they're gonna fail in bearing under a general global failure, right? So like we saw in week 5, this whole thing is gonna slip like that, okay? So that's global failure. Now, another thing that can happen in the case of loose dry sand is local failure, right? So to be honest, I don't actually know how this works entirely, but it fails in a different way, basically, right? So instead of a global failure, you kind of get a localized failure where it doesn't. Yeah. Anyway, just you can Google it if you want. But this is like local failure, and this applies for dry loose sand. So we basically have to modify our value for. We have to reduce our value for our cohesion strength, and we have to reduce our frictional angle, which also subsequently reduces its shear strength. Okay. All right. Do you guys have any questions? All right. Let's do the quiz, guys. All right. Just give the QR code a scan. We've got. All right. Is anyone else joining? I'll give you guys a few more seconds to join, eh? All right, you guys all joined up? All right, I'm gonna start. 3, 2, 1. Okay. Good luck. Oh, you just missed it. Sorry, you just missed the quiz. Yeah, okay. Anti-cheating. Did someone Google? Did someone ChatGPT?
Why is this for the cracks?
Sorry?
Is this for the cracks?
Yeah. Sorry, I'll just give you guys a bit more time until most of you are finished. right, maybe 30 more seconds. Oh, I don't know if that's too long. 30 seconds or less, depending on how long it takes for people. Okay, sorry guys. I'm gonna have to end it soon. Sorry guys. I'll have to end it soon. I'll have to end it soon now. Okay. Sorry. Alright. Congratulations, Seth, Peyton, and Jade. I think I know where you are. Okay, so we'll quickly review it and I'll give you guys a break, alright? So, alright, yeah, good thing everyone's feeling great, you know? Except for these people. Okay, so I think everyone is right on the money for shallow foundations. Yeah, piles have the pile count, but it doesn't imply that they're shallow. Okay, so basically the depth is from the surface to the base of the footing in the context of Hansen equation. For a strip footing, basically, okay, I'll tell you the correct answer first. So from the surface to the base, we know that depth is 3 meters. Width is this dimension that we can see, 4 meters. And then lowercase d is from the base to the water table. So length for a strip footing is, we can assume it's like so high that we're going to do our calculations per meter run. So these other ones that include L are not relevant. So length is going into the page, right? In this example, is the water table far enough below the footing for us to ignore the effects of a groundwater table for drained analysis? And the answer is no. We can't ignore it because basically this formula, right? So if lowercase d is greater than b dash, then yeah, we can't ignore it. Well, I can't remember like the order of okay, let's work through this, all right? What did I say? For us to ignore the no, since b is greater than d is greater than, did I do this wrong? So did I say the wrong? I think I said the wrong answer. Okay, sorry guys, sorry. Okay, I might have screwed some people over. I think it's this, right? So you have to, we can't ignore it because for drain analysis, this should be less than, I think. Whoops. Okay, yeah. All right. My bad. Okay, in this question, which variables can be cancelled out straight away? Okay, and the answer is basically we don't have any ground. We don't have any inclination factors, ground factor, or base factor, and we also don't have cohesion because this is sand. Okay, and also it doesn't imply that there's any cohesion, so we can cancel those out. Shape factor we can't cancel out because we don't have a strip footing. Because it's 1 by 5 by 1 by 5, which means it's a pad footing, right? And then for depth factor, if it's embedded in the ground, it has a depth. It has a depth factor, so we can't get rid of that. And soil surcharge as well. Basically, from surface to there, we'll have a certain amount of soil surcharge, so we can't cancel that out either. Okay. Which variables can be cancelled out straight away? Okay. Basically, I made this as an example of something that so much of the stuff can be cancelled out, right? So the idea is it's on the surface, right? So if it's on the surface, we don't have a depth factor. It's a strip footing. So if it's a strip footing, we don't need a shape factor. Did I say that? I can't remember. But basically for a strip footing, you can cancel out S entirely, right? And these ones are the same as before. This is the same as before. Soil surcharge. Additionally, because it's on the surface, we don't have to account for soil surcharge either. Okay, because there's no surcharge coming in to confine the pad, the footing. Okay, and this applies to loose sand. Okay. All right. I'll give you guys a break, and while you guys are having that break, I'm going to fix up that question for the next class. We're gonna run through some examples now, all right, for bearing capacity. So the first thing here that we see, so I've actually included all 6 examples from the workshop today, and there's like full work solutions and stuff. But I'm only gonna go through probably 3 in detail, all right? But I want you to understand the process, so I'll go slowly at the start, and then for the later examples, there's like those niche mix-ups, as I mentioned, right? So there's many ways you can mix things up, and you'll see them. Like for example, they might randomly add like an inclination factor or like a ground slope factor or whatever, right? Okay, so for this first one, a section through a long strip footing. So that's the first thing you gotta realize is that it's a strip footing is shown, and on one side of the footing, a slab exerts pressure of this on the foundation, while on the other side, it's unexcavated, so it has all this. The foundation soil consists of a clay layer having these properties, right? So it lists your drained and undrained properties. The water level is 0.4 meters above the base of the footing. Determine the maximum allowable force which could be placed on the footing, assuming a factor of safety of 3. So you basically have a footing, right? And then there's 2 sides like that they show of this footing. So you have to consider 2 different loading scenarios, like and you're designing for whichever one's worse, the one on the left or the right. Yep.
No.
Okay, yeah. And then also you have to consider drained and undrained analysis. And from all, so basically it's like a tree diagram, right? You have scenario 1, 2, and then A and B, right? So A and B might be left-hand side, right-hand side. Oops. And then 1 and 2 is drained and undrained. Okay, so you have to consider all 4 of these and then find the lowest bearing capacity. And the idea of the lowest is the one that's the lowest fails first, right? Okay, so here's a redrawn version of what they said, and here's the material properties that they said. Just remember that for undrained, they denote it with a subscript U, and for drained, they just denote it with the apostrophe. Okay, so Hansen equation, right? I want you to think about, from what you just heard, what is going to be cancelled out, okay? So we're going to look at drained analysis first, right? So in the context of drained analysis, what can be cancelled out, okay? So just give this 5 to 10 seconds of your thought, and then I'll tell you, okay? Because half of doing these questions is just figuring out what to cancel out at the very start. Okay, so what you can cancel out is there's no I, G, or B, right? So that's cancelled out from everything to begin with, right? Next, you have to remember that it's a strip footing, okay? So because it's a strip footing, all these factors become 1, okay? And you just have to trust me that that's the case. I'll show you, it makes more sense when I show you the formulas for them when we're dealing with like a rectangular pad or something, right? You'll see that if it's a strip footing where we have a really large L, the L basically makes the portion, So basically it's like L is like something over L is equal to infinity, I believe. with zero, sorry. Because the idea was if L is like goes to infinity, that portion, right, is zero or something like that. I can't remember. But basically, with the formulas for S factors, you can cancel them all out to be 1 for strip footings, okay? All right, the next thing is you have to consider, okay, so you basically have to consider the rest of them, okay? So our pad isn't sitting at the very top, right? So if it was sitting at the very top, we wouldn't have depth factors and stuff like that, but we do, okay? All right, so that leaves these ones, right? We have this portion, which is related to cohesion. We have this portion, which is related to surcharge. And we have this portion, which is the self-weight or unit weight. Okay? So that's C, Q, and gamma. That's how you can remember it, okay? All right, so from the table, so we're given a friction angle, right, for this soil, and in the drain case, it's 25. Okay, so what we have to do is we have to go to this table, right? What does this table look like? And here's where we have to familiarize ourselves with this table. This first table, I'll call it the N factors table, okay? So these are just, N factor table, N factor. This is just a table which you input a friction angle, let's say 25, and you get back NC, NQ, N gamma, and this component, right? So what is this component? It basically gets plugged into a depth factor related to surcharge. Okay, so it's a surcharge depth factor, and whenever you're using the surcharge depth factor, you have to take this from the table as well. Okay, so these numbers were 20.7, 10.7, 6.8, and 0.31. Okay. So if I take that and I move it down here, okay, you can see how this all plugs in, right? So we're just taking these numbers directly from the table, right? Okay, so next we have to calculate our depth factor, right? So when you're considering depth, right, you have to consider the most, what do you say, how do you call it? You have to consider give me a sec. You have to consider the most conservative scenario. Okay, so if on the left and the right, we have a depth over here of 0.4, and then on the right, we have a depth of 1 meter, right? Basically, you have less embedment when you have 0.4 on the left, okay? So we're going to use 0.4 for everything. So whenever you see D, plug in 0.4. Okay. Whenever you see B dash, right? This was a question I had in the break, right? So we know that the width for the strip footing is 1.5, right? But we can also see that it's not loaded eccentrically, right? So there's no offset in this loading, right? And so whenever you see B dash in these formulas, you're just taking B, right? Because when there's no eccentricity, you're just considering the entire depth, okay? The fuck, how do I close this? Okay. Does that make sense? All right. So basically we just take that width that we just saw, which was 1.5, and when you see B dash, you plug it in, okay? Okay, this thing, we just plug in, and we knew that from before. There's this funny thing I want to point out, and that's whenever you look at this table and you see the depth factor for unit weight, it's always 1. So if you want, you can always cancel it out at the start anyway. I just want to show you that. So this is always 1, right? And I'll show you the table. Depth factor is always 1. Okay, so up to you on whether you want to cancel that out or not. It's over here. Yeah? Okay. But these two you have to calculate, right? So you have to calculate the depth factor for your cohesion component, right? And this whole thing adds up to be 1.1.07. And then this one is 1.083, okay? So that's the two depth factors which are non-1. Does that make sense? Okay. So now we're considering the surcharge on both sides, right? So we want the minimum surcharge on both sides, right? And on the we know the water table is over here, right? And we know on the left we have surcharge of 20, right? So if you have more surcharge, in the context of Hansen equation, it gives you a higher bearing capacity. So if we're taking the minimum from both sides, that means we're taking the least amount of surcharge, right? We're trying to find the lowest surcharge value to plug in. Okay, so basically, if we firstly plug in gamma, right, which is just given to us in the question, is 18, and then we subtract off the water weight, right? We're given, oh sorry, they do 9.81 in this course. We're given this as the effective unit weight. Okay, and so whenever you have submerged soil, we're going to use for submerged soil for drained analysis, we're going to use this number. Okay, and then whenever it's not submerged, right? So this top 0.6 meters on the right hand side is not submerged. We're going to take the entire 18 for our unit weight. Okay. And this 20 comes from additional surcharge on the top. Okay, so that's from over here. So here's our additional surcharge. Okay, so that's 23.276 kPa. And the lower one is going to be the one on the right hand side. Okay, so the left hand side, since we have all this additional surcharge, is actually going to be less conservative. The one on the right is actually going to be the lower value, right? And we're going to take that for QO. Okay, QU, right, is our overall drained analysis. It's called drained analysis. Bearing capacity, right, for the shallow foundation. And one second. And we're going to plug in everything now that we know, right? So 5 was a material property given at the start. We just calculated QO, right? QO is 14.076. The unit weight, the effective unit weight, because this has a dash here, is 8.19. So that was from here. Okay. The width is 1.5 meters. And now we're going to plug in all of our N factors, right, which is from that table. Right, so N factors were 20.7, 10.7, 6.8. And then we have all these depth factors as well, which we calculated a moment ago. This is 1.107. QO was 1.083. And as we discussed, D gamma is always 1. Okay, so this gives us a drained analysis bearing capacity of 319 kPa. Okay. So for undrained analysis, now we're doing the second part of our analysis, right? Okay, this equation, Hansen's equation for undrained analysis, which I briefly glossed over, but I'll explain in a bit more detail now. It only applies when you have 0 undrained friction angle, right? And so then basically the Hansen equation simplifies down significantly, okay, to this. Now, something which I forgot to grab from earlier is use a different part of that table in that booklet that's provided to you, right? It looks like this, okay? One second. So for the undrained portion, right, we have different factors for everything. Sorry, these are the same as before, but our shape, depth, inclination, ground, and base factors are different, and that's denoted using subscript CU. So CU means undrained analysis, basically. Yeah, and yeah, so the equation for overall Hansen just simplifies, but we can actually cut this down even further, right? We know that we don't have any I, B, and G factors, right? And we also know that because we have a strip footing, we don't have to consider, we don't have to consider the S factor either. Now, the way that this equation is presented is a little bit different. Instead of this cancelling out to be 1, when you have a strip footing, it cancels out to be 0. Because these portions are added together, right? Instead of these cancelling to be 1, right? They don't count if it's like, so if you imagine you have some kind of number and then you're adding 0, it does nothing to contribute. But before we had multiplication, right? So if you're multiplying by 1, it does nothing to contribute, if that makes sense. So for the general Hansen equation, it works like that second case. And for the undrained Hansen equation, it's about whether you add on 0 or not. Yeah. Okay. So these are all 0. And so we're just left with this, right? Okay. So we just work out the depth, the depth factor for undrained analysis. And that in the table is just this. So we go D on B. D is 0.4 meters and B is 1.5. That gives us a depth factor of 0.1. I'm not going to say that other part out loud. All right, and then for minimum for surcharge, right? We're basically reworking this out, and the reason is because if you think about our loading scenario, right? It looks like this, and the water table was here, so that's a water table, right? So on the left we have 0.4 meters. And on the right, we have 0.6 meters of dry, basically, and then 0.4 meters of wet below the water table. But for undrained analysis, we basically consider it all with the same unit weight, right? Gamma T. So we don't do anything with effective unit weight. The whole thing's just going to be gamma T. So you can just think of the whole thing as saturated and the water can't escape from the pores, okay, of the soil. So yeah, that's basically what this line means. So 1 times 18, which is gamma T, is 18. And then we've got the surcharge, remember, on the left of 20 kPa. So that's what the thing is on the top here. Okay, so we're taking the minimum, and the minimum here is going to be 18 kPa, right? Okay, so when we plug everything in, right, so we found, this was given to us, CU. CU was 30. We calculated DCU, and we calculated the minimum surcharge, okay? And so that gives us 188.7. All right. So next, we just compare these two numbers. So this was our ultimate bearing capacity for drained analysis, and this was our ultimate bearing capacity for undrained analysis, right? And we're going to take the minimum. So the minimum's the one which is going to fail first. So we can see that the limiting bearing capacity is the undrained analysis case. Okay. So we plug that in to this formula. So this formula is telling us what is the max allowable force, basically, right? So stress is force over area, and force is stress times area, right? So this is our force. Let's call that this factor of safety, FOS. So this is the equivalent of F, right, in this equation, and this is our stress, right? The max stress that it can take, and area is 1.5, okay? So it's 1.5 because for our strip footing, our width was 1.5, and we're going into the page indefinitely, right? So what we're gonna say is per meter run, okay? So it's just 1.5 times 1, like per 1 meter run. Okay, and factor of safety was 3. So when you plug all these things in, it gives you a max allowable force of 94.3 kilonewtons per meter run. Okay, does that make sense? So that's how we calculate how much load that's allowed into the walls, basically, for this strip footing. Right. When I say walls, it's because the wall is basically the equivalent of the column. Right. Okay, cool. So does anyone have any questions right off the bat of this question? This is the slowest that I'll go for these questions. I'll start to speed up a little bit. Yep.
What did you do for Q0 again? Sorry, was you got rid of the water?
Oh, right. Okay, so for undrained analysis,
Yeah.
ignore.
For water pressure.
Oh, sorry. Yeah, basically, ignore the location of the water table.
Okay.
The whole, like, everything is going to be using the total saturated unit weight. If you want to know, like, the exact, I guess, like, geotech explanation, it's written in your booklet,
Yeah.
in the portion which is talking about undrained analysis here. Yeah. Okay. All right, cool. Does anyone else have any questions for the moment? All right, I'm going to try to speed up because I want to try to get through all these different scenarios, but we've got limited time, all right? So here we've got an eccentrically loaded strip footing, right? So again, strip footing implies that shape factor is 1. Hopefully we get to an example where shape factor isn't 1, so I can show you those equations. But basically, to get to the middle, right, we have to go an extra 0.5 meters, right, so get to 2 meters. So we know that our eccentricity is 0.5, right? We have basically a water table is near the base, which we know results in having to calculate our design unit weight in the drain case. We're given this friction angle and this total unit weight and factor of safety of 2.5. Okay, cool. So, all right, first I want you to think about what can we cancel out, all right? I'll give you 5 to 10 seconds. Just think about what we can cancel out from this loading scenario. Okay, so we have a cohesionless soil. In other words, like C is not provided because it's a sand basically. So this whole portion gets cancelled out and becomes 0, right? And then we can also cancel out the shape factor because we have a strip footing. And we can also cancel out I, G, and B. And if you really want, this thing is always equal to 1. The depth gamma, the gamma depth factor. So you can cancel that out too. So really, you only have to consider these things, okay? So there's only 6 variables, which still sounds like a lot, but it's okay, we'll work through it, all right? The first thing that I always do is I try to work out the n factors, right? And we're also going to need this because it's used in the DQ factor, okay? So this plays into DQ factor. And so if we need that, then we're going to calculate it. So from the table, right, same table as before, we're reading off of that table and we go to the row which says 40 angle, and it gives us these numbers. This isn't particularly difficult to do. Oh, I accidentally erased a 1 here. Okay. Okay, next, if we go to our depth factor table for DQ, I'm gonna show you that table again. So DQ, right? If we're focusing on this part of the table here, what you'll see is basically it says if, like, it has 2 different formulas on whether you have depth is less than or equal to your effective width, or if depth is greater than your effective width, right? So just pay attention to which one it is. and what I like to do is I calculate this first. So you calculate that, and then you plug in the formula. Okay. So you calculate the if statement first, basically, right? So we calculate the if statement, and we find that D is less than B dash. Okay. And oh, sorry, I never calculated B dash. Sorry, B dash is B minus 2E, right? So that's 4 meters minus 2 times 0.5. B dash is 3 meters. Okay. Makes sense for B dash. All right, this whole thing turns out to be 0.21. The depth is 1.5, and B dash was 3 meters, right? So when you plug all this in, we've acquired the DQ factor. Okay. Next, we've got to calculate. We've got gamma, and we've got this. Now we've got to calculate Q, right? So I've been saving this one. So what we're going to do is, okay, first we look at the problem, right? We consider everything from here to here in drained analysis for Q. I've called it QO, but like it's a surcharge from of the soil to the base of the footing, right? So because the water table is below all of that, we don't have to consider any kind of effects due to poor water pressure, right? So if the water table was above, we'd have to do some weird calculations, right? Okay, so basically we just have 1.5 meters depth. Oh, I already drew it here. Okay. So this was 1.5 meters deep into the ground, right? And then we multiply that by gamma, which is 20. Okay, so that gives us 30 kPa of surcharge. All right, so here's the thing. Now we're calculating gamma design because of the effects of the groundwater, right? So gamma dash, we actually do have to calculate, right? So okay. Gamma was 20, right? So we go, gamma dash is equal to gamma minus gamma W, right? So we go 20 minus 9.81, right? Which gives us, oh, sorry, I did it over here. Okay, sorry. It's 20 minus 9.81. Sorry, I'm not following my own working out very well. Basically, this is this box here, okay? And then for D, right, that's this depth here, right? So from the base of the footing to the top of the water table is 1.5 meters. And then the effective width we calculated before was 3. We're multiplying that by 9.8. I can't remember if the bloody unit weight of water in this course is considered 9.8 or 9.81 in the calcs, but just do a double check of the working out, because sometimes I do 9.8, sometimes I do 9.81. Okay, that is all equal to a design unit weight of 15.1, right? And so that is that basically. That becomes gamma design, which is 15.1, okay? The effective width was 3. The surcharge from before was 30. And these were all our N factors, which was 64.2 and 79.5. And what else are we missing? DQ. So DQ, our depth factor was 1.105, okay? So now we've got everything ready, and we plug that in, and we get 3,929 kPa, okay? Now we can find the ultimate amount of force, right? Which is, force is just stress times area, right? And our stress, or bearing capacity, 3,929. And our area is basically our width, which is, I keep doing this in a different way. Okay, sorry, so 3,929. Our area is 3 meters times 1 meter per meter run. Sorry. I keep like mixing up how I do my working out. So the area was 3 times 1 meter, for example, right? That gives us 11,000 basically kilonewtons per meter run. And we chuck that in here. And our factor of safety was 2.5 in this question. So this gives us an allowable force of 4,715, okay? Okay, any questions so far? So that's the effects of eccentricity and that water table thing.
They use 9.8 for the calcs.
Oh, they use 9.8? Okay. Okay, thank you. Yep, so just use 9.8. It varies between different courses in civil engineering. It's really annoying. I think in fluid mechanics it's 9.81.
Yeah.
In soils, I think it's 9.81.
Yeah.
And then in geotech it's 9.8. Okay, so do 9.8. In structural it's 10. Like for the concrete courses and stuff. You just multiply, just round it to 10. Be more conservative. Okay. Yeah, I prefer it as well. It produces nicer numbers, right? Okay. So now we can see quite a unique example. Like you'll never ever see a footing like this in real life, where it's on the surface of the ground, on loose sand, and it's circular. Like this is the most lecturer example for a bloody like impractical scenario in real life, right? So it says there's a 3 diameter circular footing which is going to be constructed on loose dry sand, and that loose dry sand has a initial friction angle of 30, but we're going to reduce it due to the design equation, this one here, and there's a unit weight of 16 kilonewtons per meter cubed. Okay, calculate the ultimate bearing capacity. And what is B saying? Oh, it's saying okay, what if you embed this footing 1 meter below the ground? How would this change the ultimate bearing capacity? Okay, so I want you to think about what's cancelled out, okay? We're looking at this formula here, okay? So just give this 5 to 10 seconds of thought. I'm going to take a sip of water. Okay, so basically, because we have loose dry sand, it's implied that we don't have any cohesion, right? Because that stems from like clay in your soil, right? So that becomes 0. The next thing is we don't have any inclination, ground, or base factors. And give me one sec. We also, okay, because this is on the surface, right? Not only does our depth factor get cancelled out, right? These get cancelled out to 1, but also our surcharge, which relies on confinement from like soil due to the embedment, is 0, right? So this actually also cancels out to be 0. So all we're really left with are these components here. Yeah? So when you have something right on the surface, you lose a lot of these factors. Like you can shed them off basically, right? Okay, so what we have to do is we have to use this formula, right? And we plug in our friction angle of, I believe it was 30. And that gives us it gives us a design friction angle of 21 degrees. Now, if you pay attention to this table, not that one. Okay, I'm going to scroll all the way up. If you pay attention to this table here, you'll see that 21 isn't like a nice round number that falls onto this table, right? So what you have to do instead is you have to use these disgusting equations, right? So like basically your plan A is use this table, right? And your plan B is use these formulas, right? So you only use the formulas if it's not on the table. Do you know what I'm saying? Okay. So we have to use these formulas, okay? All right. So, where was I up to? Oh yeah. Here are these disgusting formulas. So, if we plug in 21 degrees, which was our design friction angle, into these. Oh, sorry. By the way, with these formulas as well, the other annoying thing is you have to calculate it in a specific order. So, this one has to be calculated after this one because it's dependent, right? Do you see what I'm saying? So that one has to plug in there. So that's why like it's also even more annoying, right? Okay, so we're plugging these in, and we get an NQ value of 7.07, which we can then use over here to get 3.5. Okay, makes sense? Okay, so now we've finally calculated these by hand, which is really annoying. B dash, there's no eccentricity, so that's just the regular width, and the length is 3. Okay, so this seems a bit stupid, but basically, if we're looking down at the circle top down, right? Like we said, diameter was well, do diameter is like this or something, right? Diameter was 3 meters. Do you go I'm going with this? Like, B is 3, D is, oh sorry, not D, L is 3. Okay? So it's like the greatest width and length in that direction, which is just the diameter. Okay, that ends up being 0.6. And QU QU is our ultimate bearing pressure, right? And so we're plugging in the unit weight, we're plugging in the width, the factors we calculated, which gives us 53.28 for our ultimate bearing pressure, right? Okay, in scenario B, what we've done is we've embedded our footing 1 meter into the ground now, right? And this means that we now have a surcharge, and we also have to account for our D factors. This one is still 1, the one on the right, but we have to calculate DQ, right? Which means we also have to calculate this thing by hand, which is annoying. Because normally this is from the table, but we have a unique angle of 21. Anyway, so surcharge, right? We know that unit weight was 16. Give me 1 second. So this is 16 kilonewtons per 16 kPa, and we have a SQ factor of 1.384. Okay, so this is probably one of the clearer examples of me calculating SQ, because for the previous 2 questions I've been calculating strip footings, right? So here, when it's not a strip footing, it's a circular footing, you can see that it gives you a number that's not 1. Okay, so yeah, DQ, we have to calculate all this annoying stuff, and this is the formula that we use if D is less than B. This depth is 1 and B is 3, giving us 1.105. We can now plug in everything. So surcharge 16, unit, oh sorry, that portion on the right doesn't change from part A. These were the variables we just calculated. Okay, and that gives us 226.3, right? So this is about 4 times bigger than part A.
Real quick.
Yep.
So B and L should just be the same because it's a circle, right?
Yes. So
And
yeah, it's the diameter. Yeah.
Does that like stay somewhere?
It's kind of funny, right? Because some stuff isn't stated like explicitly in like instructions, like in that booklet, but you find them out by doing the questions, or at least that's how I validated my assumptions, right?
Is there like ever eccentricity for certain?
Yes. So that's a good question.
Would I just increase the certain to this?
Yeah. So like you know how I've been talking about the concept of B dash,
Yeah.
right? In the basically, if we have something like this, right, where the load is applied here, this reduces the B in that direction. But if we also have like an eccentricity the other way, right?
Yeah.
Say it's like there as well.
Yeah.
Do you know what I'm saying? Like,
Yeah.
you have to account for eccentricities in the B direction as well as the L direction.
Okay.
So for our shape factor, you'll see it's actually a ratio of B on L dash, I think.
But if I only reduce it, so it becomes an oval if it's only one way.
I think what you'll find is like
They won't
they'll only say circular strip footing. They won't say oval. What's more likely is a rectangular strip footing. Oh, sorry, not strip footing. A rectangular pad footing, where the load might be applied at a certain eccentricity, right?
They probably won't ask that, right?
They could ask for a rectangular footing. That's not uncommon.
Yeah.
But I doubt they would ask an oval.
Yeah. Okay. Sweet.
Yeah.
No, if you just only have it one way, and you're saying if it's only eccentricity in one way,
Yep.
does that mean the other way is still the same length?
Yep.
So it's still L3 and then the other way?
Exactly.
Half.
Yeah. So if this is like that, then L is still 3.
That would change it to an oval shape, right?
It behaves as if it's an oval. Like it would behave as if it's an oval, but it's not physically an oval.
Okay.
It's like your effective area is basically this. Do you know what I'm saying?
Yeah.
The idea is where you position the load is going to. Okay, it makes more sense on a square, right? So if we're looking at a pad footing, top down.
Yeah, that's alright.
No, yeah, it's all good. I just want to run through this, right? So that's our column load going onto our pad, right? The effective area is the whole thing, right? But if we do the same thing, but the load's applied over here, this is our effective area. Do you know what I'm saying?
Yeah.
That's what we're saying using our B dash calculations. We're saying less of the area is useful for resisting for giving us bearing capacity.
Thanks.
Yep, no worries. Okay, we're low-key out of time, but what I'll promise you is what I'm gonna try to do in the next class, right? Is I'm gonna be like clever about how I choose the questions. So instead of choosing questions 1, 2, 3, I might choose like questions 2, 4, 5, and 6. And then in my recording, I'm going to splice them together. Okay. So the questions that you missed, you can go back in the recording and see them. Okay. So question 4, basically what we've got here is an inclined column, right? So we have P coming in at a certain angle, right? And we have a square footing, right? It's sorry, where does it say? Okay, I don't know where in this paragraph it says it. Oh, okay, no, sorry, it's implied. Okay, so this thing is 3 meters by 3 meters, and it has a water table sitting 0.5 meters below the surface. Okay, there's a factor of safety of 4. So what I want you to do is I want you to think about the Hansen equation and what factors cancel out by looking at it. Okay, so I'll give you 5 to 10 seconds to do that. Okay. So the first thing you got to realize is that this soil has a friction angle, but it doesn't have cohesion, right? Which implies that it's a sand. Like if it has cohesion, it basically specifies it for you, right? So because of that, this first portion of the equation becomes 0. Okay, so we have zero cohesion. Okay, the next thing is that we don't have ground and base factors, but we do have an inclined load factor. So that is something we do have to consider. Okay, so that's the mix-up of this question. So if you look at all the workshops and all the finals, they find one or two things to mix up the question. Okay, and so you have to find out how to do the question based on all these little variations that they might put in. Okay, and yeah, I believe that's the only thing that gets cancelled. Okay, so what we're gonna do is, I don't really need to show you the table again, right? Because this table, remember that table? It has your friction angle, and it tells you all these different angles it comes from. And then where it says 30, you read across and you find NQ and you find N gamma. And then there's also this other one for 2 tan angle, etc. Okay, so that's where you get these numbers from. Okay, so 1, 2, 3, 1, 2, 3. Okay. The next thing is your surcharge. Okay, so essentially, right, we're operating in this region for surcharge. Okay, so we care about the soil that's from the surface to the base of the footing. So basically, it's the embedment, right? The embedment is 1 meter, and we know that there's 0.5 meters of dry and there's 0.5 meters of wet, essentially, right? So what we're going to do is, well, here what I've done. Here what I've done is I've taken the entire thing. Okay. I'm going to draw this out. Okay, so I've taken 1 meter of just unit weight, right? So 1 meter of unit weight, and then I'm subtracting off 0.5 of water, gamma water. Okay, so that gives us the surcharge. So this was 19, and this was 9.8. 14.1 kPa. Okay, so that gives us 14.1 kPa of the surcharge. Okay, so for our shape factors, right, we have a square footing, so we can't just turn the shape factors instantly into 1. So they follow these formulas, right? So for width, right? Sorry. Yeah. So we don't have an eccentricity. So basically we have a 3x3 square footing, and our friction angle is 30. So we get a SQ value of 1.577. And we do a similar thing to get S gamma. Okay? Cool. So, remember, to get DQ, we have two formulas, right? We have to check whether the depth is less than or equal to the effective width or greater than. So here we've seen that depth is less than the effective width, right? And so we're using this formula for DQ. This thing we found from the table to be 0.29. And then we plug in a D value of 3 and a B value of 3. Okay, and then D gamma is always 1. So this gives us 1.0967 for our DQ. All right. All right. So for inclination factors, right? This is to do with diagonal loading. Here's what I've kind of realized, right? So this formula is the most annoying thing to look at ever, right? You got to stare at it for a little while. But the idea is that here we've got an inclined load on a flat ground, right? And then here we've got an inclined load on a sloped ground. Okay, so this is case, let's call it case A, and this is case B. So we're operating on horizontal ground, which is case A, and not for the slope ground, okay? So we're going to use this formula up here, right? The other thing that you might see and be like, what the fuck is this? Is CA. So CA is a little bit different to cohesion, right? So there's C, which is cohesion, and then there's CA, which is adhesion. Okay. Does anyone know the difference between adhesion and cohesion?
Is it against the concrete and soil?
You're pretty much right. Yeah, you're right. So you'll see this pop up in the piles topic a little bit, right? Cohesion is basically the material property where where a material is able to stick to itself. Okay, and then adhesion is like what you said. It's ability to stick to something else. So right. So for example, a clay has a certain adhesive property in which it can stick to concrete, right? For example, so that's two different materials, right? But the thing is about these values, right? So let's just say we have 100 kPa of cohesion, right? Adhesion's always less than or equal to cohesion, okay? So this could only be 100 or less. So sometimes you might see it like they'll give you some kind of fraction for it or whatever. And it depends on your particular topic that you're analyzing. Like the piles topic has a specific way of calculating adhesion from cohesion, but there's like different approximations for adhesion and cohesion and stuff. Okay. Anyway, point is, because if this cohesion value is 0, then our adhesion value is also 0 because cohesion can't ever be greater than adhesion. Adhesion can't ever be greater than cohesion. You know what I'm saying? So that thing becomes 0. All right. So now, right, we just ignore this component. If we ignore our adhesion, so if we have 0 adhesion, this formula actually simplifies by quite a bit, because if you think of the right angle triangle of force components, right? We have our vertical component, and then we also have our horizontal component, right? If we have this angle to be 15 degrees, right? Our horizontal component is just going to be the opposite, right? So P sine 15. Our vertical component is just going to be the adjacent side, right? Which is cos 15, right? So our formula just comes down to this, and when you don't have any adhesion, these values for the force actually cancel out with each other within this formula, right? And then we can get a I value of 0.487. Okay? All right, now we have an I gamma value, and it's very similar. The formula is very similar. We're just going to punch it in, and so we get these two values, okay? All right, this is very important, okay? So if you have an inclined load, right? That's the I factor. And if you have a strip footing, if you have something other than a strip footing, you have an S value that's not 1. These two factors cannot be used together, okay? For whatever reason, right? This is a very particular case. So you have to check for both and find the minimum, okay? So that's what I'm trying to say here. Mathematically, right? What we're doing is we're looking at a case where you include S, and then in a case where you include, let's do that in a different color, where you include I, okay? And we're trying to find the smallest version of both of them together, okay? Now this is like a tiny footnote in your big book of geotech notes, but it's like super important, right? Because if it's in your finals, this is gonna give you the wrong answer if you add them. If you multiply them both together. Okay, so this is important. So we're just plugging everything in as we did before. And for the top case, we get 575. And the bottom case, we get 213. So when you're comparing these numbers and you're talking about something's capacity or strength, right? It's the lower capacity that governs, right? The idea is that the one that's lower gets reached first, right? Okay, so now we convert this to the soil capacity in terms of force, right? So we multiply it by the area, and it's a square footing, right? That's concentrically loaded. And so the whole thing's effective, right? So A is 3 by 3. The allowable vertical load, right, is basically just the vertical component of that. So this is gonna be really fucking trippy, right? So we're looking at this top down, right? But essentially we have a column that goes like that, right? Yeah, so that's the elevation view. And that's the plan view, okay? So we have that force. Sorry. How do I say this? Okay, basically Okay, let's draw it like this, right? This is QU, right? It's the soil's reaction to this force, right? So that's vertical, right? The soil's reaction, even if it's an inclined load, is vertical, right? So this is this, okay? And in terms of an allowable load, we're dividing it by the factor of safety, right? So basically we're equating this to this, right? And where that is QU over 4, okay? And that is QU over 4, okay? What we're trying to work out is PA. So what is the allowable load, vertical load, if it was inclined, right? So what diagonal force there is allowed such that this vertical reaction doesn't breach a certain number, okay? So to find out that, to find out this, basically, we're going to divide by that. We're going to divide by the adjacent side, right, which is that. Okay, so this is very particular to the question and how it's worded, right? But this question in part B says, assuming that you have a friction angle of 0.6 times your friction, like the friction angle of the soil material, right? So the friction angle between the soil and the footing is that, right? Is there a possibility that the footing could slide laterally under the inclined load? Is there any resistance against this sliding failure from the soil adjacent to the footing? And this brings me back to what I was trying to tell you guys about in week 5, right? The idea is that, okay, we're going back to the pencil and rubber example, right? So you have a piece of paper, you have some writing in pencil on it, and you get your rubber and you lightly scrape it, right? You're not putting very much normal force onto the pencil and then onto the page, and when you're sliding it around, it doesn't produce much friction, right? So that's the pencil and the rubber and stuff like that, right? And this page. If you have a larger normal force, right? Let's call that normal force N, right? It produces a larger frictional force, right? So the force due to friction is some number, right? Multiplied by your normal force, okay? So the same concept applies when we're talking about anything that's sliding or is resisting friction, right? But it's sometimes worded differently. So instead of mu in this case, we're going to be talking about it in terms of tan delta, right? So tan delta, where delta was 0.6 times the friction angle, right? Where that was 30 degrees, right? Gives us some kind of, I didn't calculate it before this, but this gives us some kind of value for mu, which is less than 1, but greater than 0, okay? So that's basically our coefficient of friction, right? That we're just basically working out. Okay. So that coefficient of friction goes here, right? So that's the equivalent of your coefficient of friction, and then V is our normal force, right? It's the normal component of that diagonal, right? And that is your frictional resistance, right? Sorry. Yeah, so that's the sliding resistance. Okay, and then HA was the allowable diagonal force that we had from before, and we're saying that if this is the disturbing force, right? Since this is less than this, our system doesn't move. Our system doesn't slide. Okay. All right. So does that make sense? Okay. Here I'm going to show you another example. We're not going to get to the we're not going to get to the sixth example today, but I'll try to cover this kind of quickly. So this one is actually not too difficult. The only thing that's really unique about this particular question is that there's a proposed excavation. So you can see how your formulas for G kind of manifest, right? So before the excavation happens, right, we don't have to look at G. So these get cancelled out because in part 1 it says before excavation, right? So we just calculate it as is, right? And there's nothing particularly unique about this example. But in part B of the question, it says after the excavation has happened, right? Now we have this as a complete void, and we have to basically include our G factors, right? Okay, so G factors have pretty straightforward they have pretty straightforward formulas, right? You're just plugging in that angle of excavation whenever you see psi. And the funny thing is that GQ and G gamma actually have the exact same formula, so you get the same number. Okay, so yeah, you only really have to do one calculation because these things are equal. Okay, so that basically results in a reduction, right? Because these modification factors, right, if they're less than 1, they're going to reduce your bearing capacity, which makes sense, right? So what it's saying is that this component gets reduced by about 20%. This one gets reduced by about 75%. And then this one gets reduced by also about 25%. 75%. So you lose a large amount of your bearing capacity, right? Okay, and in this last example that I'm just going to show you, right? Don't panic, all right? This is like pretty unlikely to pop up in your finals, but I'm just going to show you it in case. Okay, so a combined footing, there's quite a few things happening, right? The first thing is that before, we've only looked at, say, an individual footing like this, okay? And maybe it would have been eccentrically loaded, like this, okay? But all in all, we just assume that this basically results in normal force only, right? Sorry. There's like an effective portion of it, and then that's our QU, right? But if we have a combined footing, right, where we have multiple columns like this, the idea is that not only do we have sorry, let me just draw this first, right? Not only do we have forces that are happening on this pad, but we also have a moment, right? Basically, this is causing an overturning as well. So you have to find the pressure distribution from the footing. And then we basically have to get, like turn it into a uniform soil pressure. with, sorry, what am I trying to say? Okay, look here, I didn't prepare for this question since like 2 years ago, so I forgot exactly what happens. But essentially, I think the question says something like there's no eccentric loading, right? So if there's no eccentric loading, it spins about the middle. And so, but you can find the optimal length for this. So basically they don't tell you what dimensions there are, right? So L and B, right? You're designing the length and the width, right? Oh yeah, sorry. Well, I remember what the question was trying to say. It's trying to say, what is the optimal length and width such that there's no eccentric loading, right? So there's no eccentric loading. So the middle is where it, where the equivalent force goes down, right? And you're taking the sum of the moments, right? And that's how you work out algebraically that optimal length, right? And then you're basically treating this like a big rectangular footing, right? So you're still treating this as like L, still treating this like B. And there's no eccentric loading, so L dash is equal to L, B dash is equal to B. And then you basically get your, what do you call this? Your bearing pressure, your ultimate bearing pressure as a function of your width, right? And then you can work out width using basically saying that all the forces going down are equal to all the forces going up. And then B is a cubic. Just keeps getting worse and worse. B is a cubic, and you can solve the cubic however you like, but the way that I do it is basically on my calculator. You can basically type this in the left-hand side. You punch in a value for B that is a guess, and then you try to get the calculator to spit out 1,250. So that's how you find the roots, right, of a cubic function, right? So for example, if this is an xy plane, right, and B is your width, right? B is your x dimension, and y is force, right? If your cubic looks like that, okay? If your cubic looks like that, you have a negative value over here of negative 1.186. You have some value that's reasonable of 1.348. And then you have some value that's not possible because it would result in a B value that's greater than your L of like 9.838. So you're trying to find this value for B, which is the root of this cubic, right? And one way you can do it is if you put in your calculator, so for example, you put in 1 as a test value, and then it's too low or too high. You put in 2 on your calculator as a test value, and then it's too high or too low. Then you try in between it, 1.5, and then you keep testing values until it basically lands on 1,250. Okay, so that's how you would find the root and therefore the width. Okay, so that was like a really stupid example, and I doubt that you'll get it. I mean, it was an exam 2013 question, but we're like over 10 years away. We're over 10 years since 2013. So I doubt we're gonna get these kind of questions in your exam. Okay. All right. Do you guys have any questions? Because otherwise, I think we'll call it there. Yep. 4 for what? Oh, for L? Oh, sorry. Okay. I didn't explain that very well at all. Okay. So the question was, how do we get 4? So basically you have a combined footing, right? And you know some dimensions of the loading, right? You're told whatever the load is here. You're told whatever the load is here. But you're told like these dimensions. But what you're not told is L. Okay, so you're solving for L. And what they tell you is there's a uniform pressure distribution. There's a uniform pressure distribution, and so therefore you can actually work out L using moment equilibrium, because these forces here are equal to some equivalent force here. And then that has to be L on 2. So if we take the sum of the moments, yeah, you can solve for L basically.
It's just the 500 and 700 canceling each other out, essentially.
Yes, pretty much. Yes, exactly. Yeah. Yes, you're right. Basically, you have force 1 and lever arm 1 and 2. So we'll call that lever arm A and B. It's just whatever distance allows this whole system to cancel itself out. L. Yep. All right, guys. That's all I had prepared. So thank you very much, and good luck for your